Sure, what you want to hear, what you want to hear in space instrumentation, but I'll point to many of the space instruments in astronomy.
Yeah, that's good now.
And yeah, okay.
Yeah, ladies and gentlemen, we welcome all of us once again to today's session of the FAST4Future Summer School on Space Technology and Applications. And today is our day 4, and we are going to listen to one very important person among us, a regular person on our platform, Professor James Chibeze. James Chibeze is a professor of astrophysics at the University of South Africa and the vice chair of International Astronomical Union. Of course, Professor James is a resource person to many space instruments across the world. And it is a pleasure having such a person this morning to talk with us. So, Professor James, we are going to have this lecture in 2 segments of about 1 hour each. Well, you can determine how it goes, but we expect to have a short break of about 30 minutes in between the 2 segments so that participants can as well drink water and get refreshed to be able to take all the lectures. But if you prefer otherwise, you can still let the participants know, and then we don't have any problem with that.
No problem. I
So
think having a body break would be good.
it's okay. So I think the floor is yours, and we are all there to listen to you. Thank you.
Thank you very much, Professor Odo, and thanks for bringing the Nukuma, my boss, from wherever he was hiding before. So, uh, can everyone see my screen? Let me see what's going on.
Yes, very clearly.
Wait, but you should whisk. You're seeing it
Is
better now.
yeah,
Yeah.
better. It was diminished before.
Yes. Okay, so my job today is to tell you about instrumentation, but of course you cannot jump into instruments without understanding the fundamentals. So I'll spend a bit of time. I'm happy that I got in total, I think it's 3 hours. So I'll spend some time introducing some kind of radio astronomy. And then in the second part of this lecture, I'll talk about the instruments, the real core of what we do in radio astronomy. I had wanted to talk more about optical. I thought it would be an overkill for 3 hours to load optical um, radio as well as space science or space astronomy instrumentation in one lecture. That would be information overload. So I always like to do the thorough job. Now that you're still all fresh, no tired brains, I'll try to sink in radio astronomy into the brains. Okay. My name is James Chibueze. You can ignore everything that Professor Odo said. Just call me James. So the reason why I like to introduce radio astronomy is because right here on the African continent, we have the biggest opportunity to produce for the first time Nobel Prize in Physics, uh, which astrophysics is one of them, for the first time. And, and that could happen in the next decade or two if we take advantage of the instrument coming to the continent. That instrument is the world's largest radio astronomy project, which is called a square kilometer array. Square kilometer simply means that the collecting area of the telescope will have 1 square kilometer. It's like building a bowl that the total surface area of the bowl is 1 square kilometer. That's huge. Of course, if you have to build small dishes that are, say, like the ones you're looking at, which is the meerkat, that are just 13.5 meters in diameter, then you need hundreds of these to achieve 1 square kilometer collecting area. But already with meerkats, which has 64 dishes, we're doing absolutely groundbreaking science. We know better what our Milky Way looks like. We understand a bit more about jets. We understand a bit more about we're getting closer to the origin of magnetic field and so on. So remember, the core of my lecture will be how these instruments work. What is behind these pieces of white metal that you see that can detect the radio waves? I'll be very quick on things that are trivial, like the history of radio astronomy. Is important to know where you're coming from, then you can know where you're going. Radio astronomy's history is less than 100 years old. I always tell everyone who cares to listen that radio astronomy is the youngest aspect of astronomy. It was started in 1932. This was just after the First World War, or maybe the beginning of the Second, when people were spying on each other. Karl Jansky, who's a radio engineer, was working in a telephone lab called the Bell Telephone Labs. The real picture of the antenna he built for detecting signal from the enemies, even though we don't say that anymore, is what you see on the bottom panel there. Okay, that's the real Jansky antenna. But what he realized is while picking up some man-made signal from probably communications of maybe the enemy soldiers, he also picked up signal that was super bright, and the signal transited every 24 hours, roughly. So in the end, he was able to conclude that that signal did not come from a man-made origin, that it came from natural source. He didn't know what he was pointing at. Of course, if you know radio instrumentation a little bit well, you know that if you put together dipole antennas or put antennas the way he has put it up with wheels, the wheels is for you to roll it around so that you can determine the direction of the signal. So in principle, this has no pointing. Okay. So if it comes from extraterrestrial source, then you're most likely going to be unable to tell where it is coming from precisely. It was only until 6 years later we were able to confirm that the signal he picked up was actually emission from the center of our galaxy, from our black hole. Okay. That signal is bright and easily can be picked up with very small antennas. Actually, you pick it up every day without knowing. In the 1950s, we were beginning to build, well, of course, in 38, Groth Reber, who is a real proper radio astronomer, built the dish you see on the top panel in the picture. With this, he made the first galactic plane map, the plane of our Milky Way. He mapped it at 160 megahertz frequency. Well, this tells you how clean the Earth was at the time, right? Radio communications were still very limited. Satellite communications were still extremely limited. You could still do observations at 160 megahertz without problems. That you cannot do now very easily, okay, because there is interference. There is lots of man-made signal at at the frequency surrounding 160 megahertz. By 1950s, we have bigger dishes with which discrete sources were being identified. Of course, with a small 10-meter parabolic dish at 160 megahertz, everything is blobby. You can actually check Groth Reber's paper on the galactic plane of our Milky Way. But by the 60s, we already know what interferometry is. Of course, it took another 14 years or so for the Nobel Prize in radio interferometry to be awarded to Anthony Hewish. No, Anthony Hewish for pulsar, Martin Ryle for the interferometry. Both two persons shared the Nobel Prize of 1974. In the late 2000s, people were getting smarter. We were stopping to use hardwares for building receiver systems and for correlation and for making hardware spectrometers, for example. So by the 2000s, people were beginning to build softwares that served as receiver systems You no longer need those expensive hardwares. Well, you still need some part of computing, but most things were done in software. And it was between the time of VLA being launched, VLA coming online in the 80s, and the development of software-based receivers that the conception of the square kilometer array came on board. It was conceived in 1991. The first MOU to build the SKA was signed in 2000. I guess there may be people who were not born at the time, but last year, the first two dishes came online. So from the time the first MOU was signed to the time we started construction 2 years ago to the time the dishes started appearing on site, it's roughly 25 years. This is how long it takes you to build very large instruments. Of course, before I say anything else, I have to point you to the EM spectrum. I would have wished that I have 10 hours so I can tell you about gamma ray observations, about X-ray observation, UV, optical, infrared. Those are all interesting as well. But being a radio astronomer, I'm always biased, and not just biased meaninglessly. I'm biased because radio astronomy is super cool, and you'll see why very soon. Well, key reason, we cover a very broad band of frequency. Okay. Yes, we cannot observe from the ground for wavelengths that are longer than 30 meters in the microwave band. This is because the ionosphere would not let any radio waves longer than 30 meters to penetrate and get to us. So if you put a telescope on the ground and build a receiver that works at 50 meters wavelength, it's useless. You won't detect anything. Okay. So that opens up a way, what I always say to all the students, that you could aim to put a small radio telescope in space and observe at wavelengths longer than 30 meters and detect those emissions. And maybe you will discover new physics behind how that emission mechanism come about. So think about it as young people, not my generation. We're phasing out. So the millimeter wave, also interesting, from 1 millimeter to 10 millimeters, and then the sub-millimeter is anything below 1 millimeter. This is just what I have said. If you look at the left-hand side of this picture, you find a white line that goes all the way. If you draw that line even higher in altitude is the y-axis, then you get to a point where we call the layer of the ionosphere. Okay. Good. So anything above that, you can receive signal longer in wavelength of corresponding frequency. Remember, the top part is wavelength, the lower side, x-axis is frequency. But the key lesson to learn here is that for most of the short wavelengths up to UV, you have no option. You need to put this telescope in space. There is another strategy you can use for gamma ray, for example, what we call the Cherenkov method. You can put a telescope on the ground, use the Cherenkov shower method, and detect the light from the Cherenkov showers. And you use that to localize where a gamma ray emission is coming from. So it's not direct detection of gamma rays, but it's indirect because the gamma rays activates showers of molecules in the atmosphere and you pick it up with some kind of optical telescope. That instrument, one of the very important ones globally, is here in Africa, in Namibia. It's called the HESS telescope, high energy stereoscopic system. That's HESS. You all know about the Hubble Space Telescope. It works in the optical and UV. Some part of it you can do from the ground, but most part of the optical band, you need to go to space. The new baby in town is the James Webb Space Telescope. Of course, these are all very crucial instruments. James Webb is super important. In fact, it has already stretched how far back in time we're able to look into the evolution of galaxies and the early formation of stars. So if you haven't looked at it, please find time to look at what this beautiful space instrument which is carrying an infrared telescope, is doing. ALMA is Atacama Large Millimeter and Submillimeter Array. It's located in Chanangto in Chile, in a place you call San Pedro de Atacama in Chile. The altitude of the site is 5,100 meters. Of course, that's already above where you find oxygen. But it's, again, a beautiful instrument for studying things in millimeter radio waves. Okay, so these are all, instruments you should care about. But if you look at the radio side of things, of course, millimeter is still also radio, and we have a few places you have obstructions. In the other radio parts, everything looks clean. So the beauty of radio astronomy, lower than 30 meters in wavelength, is that we can just stay on the ground and do our science, and we can do it all day long and all night long. We don't have to wait for the sun to set to do it. While we are not obscured by the atmosphere, well, the impact is not zero. The atmosphere is made up of oxygen, the dry air we have, water vapor sometimes, hydrosols. You have a lot of the greenhouse gases, and these things do not let radio waves pass through them without obstruction. So what you see in this plot is a measurement of what we call opacity. Opacity is just how easily the atmosphere lets radio waves to pass. Okay, so the observation was done at Green Bank Radio Telescope at 1 centimeter, one centimeter precipitable water vapor. It just means the thickness of water vapor in the atmosphere is only 1 centimeter. Well, for millimeter observation, that is huge. But for centimeter observation, it's probably tolerable. So the cloud cover was about 55%. That's the condition of the observation. But you'll see the contribution of each of the components using the legend there. Water vapor is the dotted lines, and you can see that the impact of water vapor increases with increasing frequency. So as you go to higher and higher frequency, water vapor start to play a key role, because if you've done concept of scattering, if you incident a radiation on a water molecule, it will bounce back some of that radiation. It will allow bend some, okay? They will pass through the water vapor, but they will be bent. That's refraction. But of course, they will continue traveling. So the more water molecules the radio waves interact with, the more the waves are weakened. And you can see if you go to higher and higher frequency, the impact of water increases. You'll see the rest for the dry air and the solid line is just a combination of all these other ones. You may be wondering, what is the gap in between? Well, there are parts where there are frequencies at which water is excited, or what we call absorption bands, where almost everything is absorbed and re-excited by other molecules. Okay, but again, it's not optical that is completely dust extinct. We can still do some astronomy. And again, we use these values to compensate for what we have. In engineering terms, we use some keywords to identify different frequencies. You need to pay attention to this because this is very closely related to to the instrumentation we will talk about. For example, I'll say things like L band. When I say that, I just mean something running around 18 centimeters or 1.4 gigahertz. If I say S band is 13 centimeters, C band is around 6, X band is 3.5, U band is 2.5 centimeters, K band is 1.3, Ka band is 0.9, and Q band is 0.7. Remember, 0.7 centimeters is just 7 millimeters. Okay, so astronomers, I don't know, maybe there's something wrong with our brains, but we typically use this interchangeably. Sometimes I'll talk to you, I'll say wavelength. Sometimes I'll speak, I'll say frequency. Sometimes I'll use just the specification of what we call it. Like if I say C band, I just hope you will understand I'm talking about 5 gigahertz receiver system. For millimeter bands, we use band numbering. We use things like band 1, band 2, band 3, band 4, and so on. So it's not really important. I'll be mentioning the frequencies in my talk. What is good is that despite the pollution, we're still using dipole antennas. The low frequency array runs from about 1 meter to 20 meters, just 10 meters away from the threshold, which corresponds to 10 megahertz to 240 megahertz. Remember, it is in this frequency range that almost all the radio frequency transmission, your TV stations, and so on operate. So we're looking for signal very faint from the universe, but there are signals in the same band around the same frequency from man-made signal, which is much brighter than what we're looking for. Good. So I'll pause a little and answer a simple question. How much energy do you think radio photon carries? Let me take a step back. So if you know the answers, you can actually raise your hand. I'll take a step back and say, have you ever taken a picture with your cell phone? Who has? Anyone? Oops. Can you still all hear me? Chifaya.
Yes, we can hear you.
Okay, good. So if you've taken a photo with your cell phone before, what does the cell phone do? How do you capture that picture? Do you know? Yeah, Musa, please.
Right. So I think that the camera, the picture you're about to take has an emission in energy that the camera interacts with. So in terms of photon is a unit of light. So the camera tends to pick these units of light, and then, but the units of light are spread across according to the size of the camera and fixed when used together. So for each color, because light is broken into different colors, red, orange, yellow, green, blue, indigo, and violet. So all of these pixels are colors, and then they are fused together to kind of display the picture.
Okay, thank you. Julius?
Good day, Prof. The incident photon from whatever observation you're making knocks off electrons, and then that is counted as pixels. So that is what makes the picture on our cell phones.
Okay, good. So with the cell phone, you have what we call charge coupled device, which was developed by astronomers and miniaturized and put on your phones. Of course, when you take a picture, you can now later edit it. That is the same thing astronomers do. We just do it in a more specialized way. So for as the two people answered, for optical, what you have in your camera is a charge-coupled device. Yes, that's a complicated term. I know you might be thinking, what is he talking about? It's just a device made from silicon. If you're wondering what silicon is, just go outside or look below your shoes, on the sole of your shoes, pick up a grain of sand. It contains silicon. Now, silicon, if you take a quantum microscope or even a simple one and look at it, you'll see a picture you see on my screen. Okay, it's a crystal with well-organized structured distribution of electrons. Okay. Now, if you take a photon is a quantum mechanical concept that simply means that a wave can be, no, that electromagnetic signal can behave both as a wave and as a particle. So sometimes it behaves like a particle and has collisions. Sometimes it behaves in the analog way of a transverse wave. Now, if you call it photon, you cover the two of them. If the photon gets into the CCD camera, which is made of silicon, what it's going to do is to knock out, if it has enough energy, it's going to hit one of those atoms or one of those particles, which is essentially electrons, and it will knock it out from the bond. So in the bonded state, we call it the valence band. But if it acquires energy and jump out of the valence band, it goes into the conduction band. So it becomes a free electron in principle. To do that for silicon, which is what we use in building CCD cameras, then you can use the equation to the left-hand side to compute the energy that you require. The band gap in silicon is equivalent to 1.26 electron volts. Okay. So if you take 1.26 electron volts, you can use the equation of E energy being equivalent to H Planck's constant multiplied by frequency. Of course, you can exchange frequency for wavelength by introducing the speed of light. So if you do that calculation, it will come to the wavelength being around 984 nanometers. So the threshold you must have for you to be able to knock out electron, okay, it must be less than 984 nanometers. That's roughly around 1 micron. Okay, 1 micrometer. Good. So if your wavelength is much longer than this, then the photon would not have sufficient energy. It means the energy will be less than 1.26 electron volts, and therefore you cannot knock out electron. The photos you take, each of those pixels is just the number of free electron that has been knocked out by the photon that are incident that falls into the pixel. The pixel is like a cup. You collect all the free electrons and you count it, and in that pixel you write the number of electrons. So you do photon counting because well, you can call it electron counting or photon counting. Because the photon coming in to knock out the free electron or to knock the electron into conduction band, okay, has sufficient energy so you can take pictures. When you take picture of a laptop, for example, or a wall, you see the wall. Or if you take picture of your human, you see the human, not because the human is giving out light. The human is reflecting light from around his or her surrounding. Okay, cool. Now, keeping this in mind, we can go back, use this same equation, change the wavelength to the wavelength of radio waves, and see if we will still have this, at least a value that is 1.2 electron volts or above. Okay, that's the question here. How much energy does a radio photon carry? We have seen that optical photon carry energies sometimes minimum 1.26 electron volts, but is usually the rest of the frequencies in optical are higher than that. So for optical, for example, if you even go to shorter wavelength like 600 nanometers, the energy is even higher. It becomes 2 electron volts, and you can compute the temperatures. The kinetic temperatures you can achieve will be around 2000. But if you do that for radio photon, you would see that the energies are super, super low, 10 to the power minus 6 electron volts. And therefore, if you incident this radio photon, if you generate radio waves from your cell phone and you put your camera behind when somebody is making phone call and you try to get picture of the radio waves, you're wasting your time. You would not be able to get it. Yes, the radio waves are hitting your CCD camera, okay? But they are not strong enough to knock out the electron for your camera, the pixels of, that will fall into the pixels of the camera and then be counted. So counting photon in radio astronomy is not even an option at all. The energies of the photon are too weak. So how then do we measure radio waves when we do radio observations? What exactly do we do? Well, we change the strategy. We think less about counting photons because it's not possible. We go about measuring radio waves by measuring the voltage oscillations induced in a conductor by incoming electromagnetic wave. Well, this is long grammar. I'll break it down. If you pick up a radio set, the first thing you do is to pull out the antenna and then you turn it on. If you make the antenna longer, it means more radio signal will incident on every part of that antenna, and then you collect more signal, and then you get better voice quality. All you're doing there is picking up the modulations, the oscillations of the voltages, because for every signal, radio wave signal that is incident on the antenna, the active component of the electromagnetic signal is the electric field. Remember, the EM wave has the electric component, okay, and the magnetic component. That's why we call it an electromagnetic wave. So if you incident EM wave on an antenna, you induce small current, it's few voltages, millivolts of signal into the antenna. And then you can channel that into your feed or your waveguide and put it in the receiver. In the case of your radio set, the receiver are those transistors, resistors, down converters that you find inside. Okay. So in radio astronomy, we simply measure the voltage oscillations in that electric signal that is induced in a conductor by an incoming radio electromagnetic wave. Any questions so far? None? Okay. Good. So here's why radio is very cool before I go to what the instruments we use to do radio astronomy. If you remember our Milky Way, if you go online and Google Milky Way galaxy, you find a picture like this. Well, in real sense, we do not have a true picture of what our Milky Way looks like. But from measurements we have, we can tell it does have spiral arms. And what you see here is just an artistic impression of the spiral arms and an indicator of where our position in our galaxy is, because we know how far away we are from the center of our Milky Way. Therefore, we can put our position properly. If you take that circular disk at the top and turn it around, for example, if I take my iPad, I hope you can see me, and put it this way, you can see the entire square. Just in your mind, imagine that this is cut in a circular form. So you can see the full disk face on. However, if I do this, what looked like a disk, what you can only see from your perspective from my camera is a line. So this is the plane of my iPad. And if you do the same and take this image, flip it, the disk, and flip it around, then it goes in the plane direction. That's actually what we see from our vantage position here. If you observe our galaxy in optical and try to make a map of every light coming from our galaxy, you produce a map at the top. And if you do the same in radio, you produce the map below. Crucial thing why radio astronomy is cool, if you look at optical, you find that in the optical image, there are dark patches or what you call dark lanes where it seems like there are no stars or no light coming from anything that is within our galaxy. But that's not correct. There are lots of things there, but the problem is that our galaxy is made up of gas, dust, stars, star clusters, planets, and all these other things. The dust part is a problem. Okay, if the dust is in the foreground and the source star you want to see is in the background and you're looking at things from here, you will not see anything. Take an illustration if you drive around in Nigeria or if you take a bus, maybe Peace Mass for those who are in Soka or Enugu, and there is a vehicle ahead of you that is chunking out very dark smoke. You realize that your visibility as a driver driving behind such a bad vehicle or a rickety vehicle becomes very limited. So you cannot see things ahead because all the light reflected by objects ahead of you are completely absorbed by this black smoke that this vehicle ahead of you is producing. That's the same thing happening here. In the optical, they are limited due to what we call dust extinction. Dust completely cancels out the light, absorbs it, and therefore we don't see it. In radio, radio waves are not colorful. They are not white or yellow or red or blue, and they don't have sound. So if you've watched the movie Contact, where Jodie Foster pretended that she could listen to radio waves, no, there's nothing like that. You don't listen to radio waves, but you can down convert the signal in the radio wave to a frequency that is audible. If you down convert the frequency, mix it down to a frequency that can vibrate the ossicles in our ears, then you can listen to convert it to some kind of sound. Okay, but radio waves in principle are not sound. Okay, so in radio, we have no dust extinction. Radio waves will penetrate through. That is actually why it's one of the discoveries of our generation to have mobile phones. You sit inside the room with walls, no windows, you can still receive cell phone signal and make phone calls because radio waves can penetrate through concrete walls and get to you. The same way they penetrate through dust and get to us, and we can image that. So that's the cool thing about astronomy, radio astronomy. The next cool thing is that it brings us completeness to brings us close to completeness in our understanding of our universe. This is Centaurus A. It's a galaxy observed in the optical. We see a lot of dark lanes, that's dust, and you can tell the dust is absorbing the light from the background. And there is a glow from around the center, which is where the supermassive black hole hosted by this galaxy belongs. And there are a number of stars. Okay, some of them still forming, like the ones that are reddish or probably also dying. Could be anything. If we did not have radio astronomy, this is the only thing we would have known about this galaxy, and maybe the X-ray, which is a hot gas around a supermassive black hole. But this is what you see in radio. If you observe this in radio, the orientation is the same. I did not flip the direction. You will see this, make this map in radio emission, which is strange, okay? Because one would have thought at least it would align with the direction of the disk, but you can see nicely that it is perpendicular to the spiral arm or the disk of the galaxy. If you put this image together, it tells you that this is a huge galaxy with dusty disk and arms, of course, and then it's launching synchrotron jets in the perpendicular direction of the disk. So it changes the picture of what we know about galaxies that we would have thought something different. Okay, now I have questions. Ooh, okay. That reveals it. If you look at this picture, this is taken in optical. I'm sure you would say you see a galaxy that has spiral arm. You see other dotted things that may be foreground or background stars. Some of them big. One looks like Saturn. It's a bit elongated. If you had only optical, that's what you will see. you have no clues about whether there is any form of interaction between the objects in this image. But if you observe this same region with radio and at 21 centimeters, you will detect hydrogen. Hydrogen emits radio waves, yes. And each part you find red, yellow, green, light blue emission, that is distribution of hydrogen emission, okay? If it's red, it's stronger. If it's blue, is weakest, but it's there. So what you can see, you can actually start to pin things together. You can see the three galaxies, and there's a long bridge of hydrogen gas between all three of them. So in astronomy, we call this tidal interaction. These three galaxies, three big galaxies, you can match them by eye, are actually talking to each other via exchange of gas. Because of time, because I want to jump into the instruments, I'll just quickly highlight some of the emission mechanisms. If you don't know them, please go and read about continuum emission and spectral line emission. And I'm sure in your physics, you would have looked at Planck's distribution function, which is used to explain blackbody radiation, which is a thermal kind of continuum emission. If you want an approximation of the Planck's distribution function, you can always use the Rayleigh-Jean function, which is an approximation of the Planck's distribution function. And then we have Bremsstrahlung emission, which comes from ionizing hydrogen, which in principle will generate a cloud of electrons and a cloud of protons. And protons are heavier. We assume that their motion is limited, but electrons are lighter. They move around very often. And sometimes they come close to a proton and the attraction force kicks in, but they are not completely trapped. They are deflected and their path is changed. So they have energy 1 before deflection, energy 2 after deflection. The difference in the two energies is the energy of the radio waves released. And that is a thermal emission because you require heating to ionize hydrogen. But we have synchrotron emission, which doesn't require any kind of heating. It only requires you to have an electron that is moving at the speed close to speed of light. We call that synchrotron, relativistic electron, not synchrotron, sorry. So if you have relativistic electron that gets coupled in magnetic field, then each time it makes a loop in its motion along the magnetic field line, it gets a kick. So there's some form of acceleration due to the impact of the magnetic field. And this acceleration causes, of course, change in velocity, which is eventually change in energy. And the difference in the energy is released into the intergalactic or interstellar medium. Okay, spectral line, I talked about neutral hydrogen at 21 centimeters. It's generated from the change in spin direction of electron, typically spin in the same direction as the proton in the center, but sometimes it flips its spin direction to the opposite direction and releases energy. We have molecular lines that come from vibrational states of different molecules. These vibrational states can be of multiple kinds, of course, including the rotational states for polar molecules. Okay, I'll not focus on this too much because I want to go straight to instruments, but feel free to ask me questions on this. Okay. Good. Here is where the instrumentation comes. Okay. This is a simple schematic diagram, but I'm going to break it into multiple pieces, smaller pieces. The first and the most important part of your radio telescope, I'm talking this time about parabolic dishes, not the dipole antennas, is the primary reflector. That's your main dish. It's typically very large because we want very large collecting area to have very large sensitivity. If you don't understand what I mean, if you watch football with DSTV or GoTV and you have a small antenna, 75 centimeters, you realize that if it rains, even for a very light rain, your channels begin to scramble. Yes, that's normal because water itself releases radio waves and absorbs the one coming from the satellite you're pointing the dish at. So what you need is a bigger dish. So instead of 75 centimeter dish you normally use, if you want to continue watching your TV when it is raining, get a 5-meter dish. So over 5 meters, your collecting area is now 5 or 6 times larger, 5.5 or 6 times larger, and you're collecting more of this signal. When you stack it together, it will be higher than the noise generated due to the rain. So we make large dishes for collecting area, and we focus it on a sub-reflector sometimes. Sometimes we build cheaper radio telescope where we directly mount the receiver where the sub-reflector is. But if you've got a sub-reflector, you put in a feed horn, and from the feed horn, you use a waveguide. Waveguide is just something with which you transport the signal into the receiver. And at the receiver stage, the signal we have is very weak. We typically amplify it first. We call it first stage amplification. And then we start to put in things like local oscillator to mix things down and generate the intermediate frequencies. But I'll come to that. After that, we record the data, export it to a computer, do all the calibration, and do the imaging, and then we save all of the files. Any questions so far? So I had to exit full screen to just make sure that there are no raised hands that I'm not seeing. Okay, Julius?
It has skipped. I would say it later, sorry.
Okay, cool. Great. So here is one thing you need to know about the reflectors. I showed you an example here. This is what we call on-axis Cassegrain. You can see the sub-reflector is focused right at the center of the primary reflector or the big dish. Okay, so this is on axis, but it's Cassegrain focus. So that's similar to this, the one on the top right. ATCA is Australian Telescope Compact Array. Is built in that form. You can see in the inside there is a white feed horn. And then there is a sub-reflector held by the quad legs, the 4 legs holding the sub-reflector. We have prime focus. I did mention this. Instead of a sub-reflector, you just put the feed horn and the receiver at the top. We also have offset Cassegrain. Typically, you build offset Cassegrain. Let me exit so I can point. This is an offset Cassegrain. This is a VLA ALMA. The reason you do that is because you want to conserve real estate space. If you look at this closely, if you can see my screen, it's low resolution. I didn't upload a different picture. There is a feed here. There are also other multiple feeds here. So the axis, it would have been on axis if there is only one, and the signal hitting this main dish bounces here, and this focuses it on the main one, right in the center. But in this case, there are some off the main axis. The main axis is in the middle of this circle, but there is a feed horn here. There is one there. So what you do is to adjust the position of this sub-reflector, tilt it slightly so that the radio waves hitting here will be bounced into these receivers. So that's offset from the main axis. Therefore, we call it offset Cassegrain. We have the Nesmith. Nesmith's case, you just put in mirrors. Yes, in radio astronomy, we say mirror, but it's not mirror for reflecting light. It's mirror for reflecting radio waves. So you see in the center of this dish, there is a hole. Behind it, there is a white metallic panel. And that panel is installed at, say, an angle of 45 degrees or so. That way, the signal reflected by the subreflector here hits the panel and then is focused on the feed horn, okay, and then to the receiver. If you reflect only once, you call it a Nesmith. If you want to put the feed horn here, you need to put another reflector in this direction so it hits here and comes down, and then that becomes a bent Nesmith. So each of this picture and the name of this telescope are examples of instruments that use this. My favorite is the dual offset Gregorian, which is this dish, the Green Bank telescope, as well as the Meerkat telescope. Hopefully I'll show that later. They're both dual offset Gregorian. In this instance, the uniqueness is that on the main surface, there is nothing. Every other dish has a leg standing in the main surface. But in the case of this, there is nothing in the main surface. The subreflector is installed here, and the arm holding the subreflector, the arm structure comes from the outside, so that signal hitting the main dish gets focused on the subreflector, and from here, it bounces it into the feed horn, which is installed here. I know this looks tiny, but this dish, the main surface of this dish can take a full football stadium, can fit in here. So these are all the different antenna configurations that we have. Of course, all depending on how much money you have and the technologies you want to subscribe to, you could build any one of these. If you want the cheapest one, it's typically the prime focus. You get a dish, you find the focal point, you use arms to focus things on this focal point. If you don't know how to compute the focal point of a parabola, just go back to the mathematical equation. It gives you the nice arm, and there is a formula to compute where the focal point will be from the center of the parabola. Any questions? Yes, Julius.
Okay, so my question is on the electric oscillations from the antenna.
Yes.
Does it ever happen that the amplification that is done exceeds the one that is, from the formula used or something? What you receive, and then after amplification, it's too much for the amplifier. Does it ever happen?
What do you mean too much for the amplifier? Amplification is just multiplying the signal you get by a factor, right?
Okay.
If the voltage you're getting is 1 millivolt, okay? Remember,
Okay.
1 millivolt is even smaller than the noise that your receiver will produce. So the first stage amplification is to say you're going to multiply this by a factor of 10, right?
Oh,
Good.
yes. Thank you.
So you're multiplying everything by a factor so that you can be able to handle the data. There are other things we do in the receiver that I will describe soon. Okay, so if you have an antenna is a very complicated thing. Having something that is perfectly a parabola is not determined by your viewpoint. To be a perfect parabola, it must be a dish that obeys the parabolic equation. Okay. However, making that is very difficult. The dish is very huge. To install the panels in the dish, people climb on the surface, they step on the panels. If you step on it, you may not deform the panel, but you may add weights and then it depresses as a whole. So the individual panel is not dented like you hit a hammer on the surface. If you take your mom's pot or your own pot and take a hammer and hit on it, then you've dented that. If you shine light on the pot, the dented part will be the first to show you that there is non-uniformity in the shape. Okay. So for radio telescopes, when there is deformation, we hardly can see it by eye. So we perform experiments we call holography, where we illuminate the beam with radio waves from a satellite, because satellite sends out beam of very bright point-like signal. So with that, you can illuminate your beam nicely, and you can reconstruct the shape, how much deformation is in each panel in your beam. Now, because you could have deformation, it means not all signal, like you can see in the dish that is drawn there, is a bit wiggly on the surface. So it's not every signal hitting the main surface that goes to the focal point. Those things you lost decreases the efficiency of your telescope. Efficiency is just the ratio of the effective collecting area over the total collecting area. So if you have a 30-meter dish, in principle, you may be using only 50% of it when you observe at certain frequency. For the very large array, they have telescopes that are 25 meters in diameter. I think they have 27 of them. At 43 gigahertz, the efficiency of each of those dishes is about 0.44, which is just 44%. Of course, when you go to lower frequencies, the impact of deformation becomes less. So at 22 gigahertz, the efficiency is about 80%, so 0.79, which is 79%. Okay. Good. So efficiency depends on blockage. I'll go one step back again. Remember, when you calculate your total area, collecting area, you would use the diameter of this face, right? But you can see from the sun alone that if we are observing the sun, we only pick up the bright parts. Everywhere is shadowed, the signal from the sun is bounced back. So the four legs holding this subreflector shadows the signal. Okay, so you have to calculate the area covered by these quad legs and then subtract it by the total area of the dish. Of course, you also take care of the area in the center because it's not being used and the shadowed part. So in principle, by the time you remove all the shadowing or shadowed part, whatever is remaining, only that fraction is what you're using for the observation. So you can build a 100-meter dish, but the effective area you're using might just be 50%, but very strongly dependent on the frequency. So we have that blockage, the surface accuracy, which is the deformation in the surface. We have contribution from the blockage. We have contribution from what we call spillover. Spillover is when you point your telescope towards a low elevation source and the emission from the ground somehow makes it into your beam. Okay, so it spills over into the beam and it contributes into the efficiency. Tapering, sometimes you want to have lower resolution and then you taper your beam. It just means covering some part of it to use only a fraction of it. The efficiency in reflection of the metal that you have used. This here is the reason why most of the dishes you see, including your DSTV antenna, are made of aluminum. Aluminum can reflect 99% of radio waves incident on it. So don't be quick and say, no, aluminum is expensive. I'll go use iron, a thin sheet of iron. I think iron is around 84% reflectivity, and it is heavy. It's heavier than aluminum, so it's going to cost you a lot more to install expensive motors to drive these big monsters in telescopes. There's also the miscellaneous contribution to efficiency. This includes diffraction, phase errors. Sometimes your focal point is not determined properly. There's also inefficiencies in the polarization. Okay, here is a real measurement. If you go back to my earlier slide, I showed ALMA telescope. This is one of ALMA's telescope. And on the left-hand side is what the holographic map I already described, holography map of the dish looks like. You can see the demarcations, the black lines are just demarcations of the panels. So what you see in the color bar shows you deviation from zero. A perfect parabola, all the deviations will be zero. So if you write equation of a parabola or you make it in a software, in a computer, the parabola will look perfect parabola because this is equation derived parabola. There is no error. But human or engineers built parabola can have some error because you tighten the panel too much, then it's too deep. If you tighten it less, then it's slightly a few millimeters high, and so on. Remember, we're trying to study millimeter wave, therefore the accuracy must be very, very, very good. So if you check before adjustment of panel, you'll see that the average deviation is 43 micron. I know this sounds completely strange, but if you can just stick your hand on your hair, find a single strand of hair, pull it out and hold it and look at it. That thickness of the hair you're holding is 1 millimeter. To get 1 micron, you need to divide that hair into 1,000 places. Okay? Now you divide it into 1,000 places, you take 43 places. That's the error we have in the surface of this dish. This is real panel. Okay? It's real telescope. Let me escape and show you. Here is this dishes here. So the measurement on this is this result. Okay. So we're not making up stories. You point this to a satellite, you illuminate the beam, then you make the map of the deformations in the beam. And then you use this map to go individually, wherever the color of the panel is more red, it means it's too high. So you adjust it to move back down by a small fraction. Then when you have adjusted all the panels, if it's too low, then you loosen it to come back up. You adjust each panel one by one. And after that, you can improve the surface accuracy by a factor of 4, which is quite nice. You get the things on the right-hand side. Okay. You may be wondering, but no, but this dish looks nice and this. But if you're doing millimeter astronomy, you need to properly adjust your panels. Any questions? Let me see. Yes, Chidi.
Yeah, thank you, Prof. My question, okay, I was like, just it's actually taking you a little bit back. Sorry about that.
Yeah.
Does the reflector antenna have any effect on
Does the
radio
what?
waves received? Both of them are like, I'm asking, does the type of reflector antenna have any?
Does the type of reflector antenna have any effect? Remember, an antenna is just a piece of metal. If you incident radio waves on it, you generate
Yes.
millivolts of signal. Yes, it does have an effect. I stated here that the efficiency of reflection of radio waves is crucial for the overall efficiency of the antenna. So if you make your parabolic dish with titanium, for example, yes, it will reflect radio waves, okay? But if the reflection efficiency of titanium is 60%, then that impacts the efficiency of your entire dish. Julius.
Okay, thank you. Does this correction have to be done every now and then, like the last slide you showed? Yes.
The answer is yes. So people who have money have done things slightly differently. These dishes are huge and heavy. Somewhere in my Skype profile, you can see how tiny I am with respect to this dish. If you go to YouTube, maybe I should do that. Let's see. Um, GBT. Let's go. This is just to give you an idea of how large this telescope is, and how small humans are with respect to it. Yeah, this one. So this is a 3 minutes video. Can play that. I'll answer your question after you listen to this. No. I have a meeting going on somewhere else, so let me see if I...
GBT is the largest fully steerable radio telescope on the planet. It's one of the largest moving structures on land. It stands 485 feet above ground level, which makes it taller than the Statue of Liberty, weighs almost 17 million pounds. So with 16 wheels, more than 1 million pounds per wheel is transferred to the foundation.
Okay, the boat you saw there is bigger
Like
than a
a
human head.
bigger bucket collects more raindrops, the GBT's large surface area can collect more radio waves from space. The reflecting area is 2.3 acres. So a football stadium would fit inside of that.
There's something he didn't say. He didn't say how many panels are here in this. I think there are thousands of them. I can check the number and tell you later.
So radio telescopes are just one window onto the universe. When you think about astronomy, often people think about your classic optical telescope, something you can stick your eye up to and you can look through and you get to look at a picture of a galaxy. A radio telescope is the exact same idea, only instead of looking at the optical waves, the stuff that you can see with your eye, it's looking at radio waves.
We're trying to take the principles, the things we understand about chemistry from the laboratory, and apply those to molecules in space. Understand how you can build up things that lead to the formation of maybe life from what we see starting out in the earliest remnants of dead stars and the birthplace of solar systems.
The light coming from the galaxy we're looking at is about as old as the Earth is now. The GBT is especially good for this. It's so massive. Its beam is very small. It's incredibly sensitive for this kind of work.
The sensitivity of the GBT is 10 to the minus 29 watts per square meter per hertz. Now, to put that in a term that you can understand, it can detect.
Okay, so what I want you to see is how huge this thing is, right? This is a human standing fairly close, okay? And the height of the person is just slightly above the foundation. This is massive, it's huge. Okay, I don't have all the time, but you can ask me questions later. Let me come back to the question that you asked. Do we have to each time go into this telescope and manually adjust it every time it deforms? The answer is yes. Remember, this is huge. When you use it to observe after some period, the panels will move. There is huge gravity. There is also the sun. The sun shines, and if you hit, when you build a railway, you give those gaps for expansion of metals. These are metals. The sun will hit it, it will expand. And when it contracts, it may not contract back into its original form. So there will be deformation, which you cannot see with the eyes, okay? Because your eyes cannot resolve 1 micrometer or 10 micrometer change. We don't have that capacity with our eyes. So what many people who are rich have done is when they build this big telescope, they they put what we call actuators. They put things that you can use and push the panels up or lower it inside. So we call it telescopes with active surfaces. It means every panel has some four actuators behind it that when we do holography, say after every 3 months, and things have gone off, then we use the actuators to readjust them instead of going in and manually doing it one by one. If you don't have money, which runs into millions of euros, tens of millions of euros, to put actuators in each panel, then you have to manually do it each time your beam is deformed. Did that answer your question?
Yes, Prof. Thank you.
Okay. Cool. Musa, please.
Okay, thank you very much, Prof. My question is hinged on that of the material selection for radio telescope dish, maybe construction or installation. Of course, aluminum is a very good material, but it also, because of its high electrical conductivity, but it also has high thermal conductivity, which is increasing heat.
It
So,
doesn't have high electric conductivity. Aluminium has lower electric conductivity. I think copper has high electric conductivity.
all right, so as compared to other metals, because the telescope is an outdoor uh, equipment.
Yeah.
So the level of heat that aluminum conducts, does it increase or play a role in the signal, or does it affect the signal?
Yeah. So the expansion causes deformation to the dish, right? That's one of the key things thermal processes can yield. But to counter that, if we have sensitive observations we need to do, we do it at night when the sun is on the other side and all the surfaces are cooled down. What you want the most important parameter you need is a metal that reflects radio waves perfectly. And there is no other metal that can reflect radio waves better than aluminum. Okay.
Okay.
So the thermal expansion we can deal with. Yeah, but we optimize reflectivity.
Okay. So reflectivity is more of the most important thing than that of the heat.
Yes.
Okay. Thank you.
Okay. Good. So remember when I mentioned offset Cassegrain? This is a picture I took when I worked at the VLA. The top panel is the number of feed horns that are located on the VLA top. So the sub-reflector is always adjusted to focus the signal on each of these feed horns depending on the frequency at which you're observing. Okay. And if you go behind this feed and go inside the cabin, you'll see that each feed horn terminates into the receiver system, and the amplification process causes a lot of heating. Yes, I know you may be asking, how is amplifying signal causing heating? Well, an amplifier is just an electronic circuit, right? Electronic device. Just like your cell phone, if you keep it functioning, receiving signal and transmitting signal for 20 minutes, it gets warm. That's Ohm's law. Okay? Whenever you transfer charges through current flows through a material with any form of resistance, you're going to lose some of that in form of heating. Okay. Now, heat in itself is energy. It's just a bunch of photons creating energy and can get into the signal and become noise in the signal. So to mitigate that, we do what we call cryogenic cooling. The boxes you see just at the tail end of the cones are like refrigerators. we use compressed gas, compressed helium or nitrogen, and pump it in there. If you compress it and pump it in and it expands, it cools and absorbs the energy, and then you suck out the gas again, you take it out, compress it again, and pipe it back. So there will always be two pipes, one pipe coming in to supply the compressed gas and another one going out to take away the expanded gas that carries out the energy outward. Well, if you're thinking of how much temperature we cool these systems to, the receivers or the low noise amplifiers that we have in the VLA are typically cooled down to 15 Kelvin. Yeah, I know it sounds strange, but 15 Kelvin is actually uh minus 370, 273 plus 15, right? So you're thinking about something in the neighborhood of minus 200 and over minus 250 degrees Celsius. That's how low the temperatures are right in those systems. In fact, if you go to the ALMA telescopes, we cool down to 4 Kelvin. 4 Kelvin is minus 269 degrees Celsius, minus, not plus. So humans survive in 30 degrees Celsius when it's hot. During the winter, it goes down to 4 or to 0 or to minus 6, but this is minus 269 degrees Celsius. This is solely because we want the amplification process, which generates a lot of noise. Noise is just the heating to be taken away by the cooling processes. Okay. So to get perfect amplification, we use things like low noise amplifiers that uses the HFET system. It's a heterostructure field effect transistors inside, and they're used in the VLA, the VLBA antennas, as well as the GBT. GBT is a big antenna that I just showed you. And that's a picture of what the LNAs look like. This may look very boring. It's not gold. Of course, the material you're using making it, you want to surround it with metals that are lower conducting metals so that the heat somehow is preserved and cooled in one spot. So we use specialized materials. They are nicely machined. A few cheap things are done and kept off the shelf, like the LMB you buy, the low noise block you buy for your dishes for TV stations. They have low noise amplifiers inside. But those work at room temperatures. We're observing very faint signal in the universe. We want it to be even cooler, because if you're trying to measure 30 Kelvin coming from the universe and your system noise temperature is 50 Kelvin, there is no way you will be able to measure 30 Kelvin. It's within your noise. It's synonymous to saying your mom has fever and her fever is 40 degrees Celsius, and you have fever and your own fever is 38 degrees Celsius, and your mom who has fever feels your neck and can tell you have fever. That's impossible because you're cooler than her. So she cannot detect your fever. So if we want to detect cold universe, we need our receiver system to be cooler than the cold universe. That's in principle what the LNA does for us. Then there is a mixer. Handling radio frequency at high frequency band is extremely difficult. So what we typically do is to mix down this radio frequency signal to a lower frequency so that it is easy to handle in the electronics. And then we output what we call intermediate frequency bands. So a mixer is just a 3-port device that takes an input, which is your incoming radio frequency, then injects a local oscillator, which is the mixing of the signal. Just local oscillator is something generating frequency reference that you inject into the radio waves. And then it combines these two or multiplies the two and produces your intermediate frequency. So two inputs, one output. The major input is the RF. The second input is the one you generate, which is your local oscillator you inject, and then you output to the intermediate frequency. The intermediate frequency is where you play around, okay? You can put the intermediate frequency, the local oscillator can be in the middle, so you can have your lower sideband and upper sideband on both sides of the local oscillator. Okay, so from your intermediate frequency, you can play around with whatever you want to do correlation, and so on and so forth. So in the end, I did not mention all the instrumentation we have in radio. There is still what we call the noise diode. Astronomers want to measure things in Janskis, but antennas measure things in power densities in counts per megahertz. So what we do to adjust to antenna temperature is to get a noise diode, which is a source that can generate radio waves at the same frequency as the receiver, but at a calibrated noise temperature. So if you inject the noise temperature, you know the noise temperature, whatever signal you inject, you measure the power density, and you can use that to scale how many counts per megahertz in power density correspond to 1 Kelvin. So from antenna temperature, you can now use a calibrator source in the sky to convert to Janskis. So in the end, in a radio telescope, when you point it to a source, what to pick up is noise temperature coming from cosmic microwave background coming from your receiver. Yes, we cool the receiver, but we don't completely take away the contribution of noise from the heating. Okay, because we don't cool it down to 0 Kelvin, essentially, which is impossible. Okay, and then contribution from the source. You're interested in contribution from our atmosphere, contribution from our spillover, and contribution from probably residual receiver band systems. So when you take a data from a radio telescope, you want to convert from power density to antenna temperature. Then from antenna temperature, you use a known calibrator with a known flux density to scale to Janskis. You fix the impact of the band pass, you fix the error in your pointing, and then you convert to Janskis, as I said, and then you apply that to your target. Okay, so I was asked to stop at 1 hour 15 minutes. I stopped at 1 hour 25 minutes because I took questions, but I'll pause here with radio and take questions, please.
Okay, thank you so much. So James, of course, you have been taking questions, participants, but if they still have more questions, can respond to 1 and 2, then maybe allow them to have some minutes rest,
yes,
and then bounce back.
Yes, Juliet.
Okay, thank you, Prof. You mentioned our entertainment dishes make use of the low noise blocks, LNBs. Wouldn't it be ideal for the radio telescope to also make use of that, or it's just that diode you mentioned?
The low noise block is just the amplifying system for the signal, and the signal you're pointing to from your television dishes is very bright. So you don't need to cool it down. You don't need to cool down the low noise amplifier. Okay? Because
Yes.
this is a beamed signal from a satellite is 1,000,000 times stronger than the signal from a galaxy 1,000,000 light years away, for example.
Okay, thank you, Prof.
Yes, so there's no need for cooling. Well, but you can still use, I can't demonstrate it now. I wish I can teach this module in person. I've built a system that uses 2 small TV stations and points to a satellite, okay? but uses the transmission of the satellite and the correlated signal between two antennas to measure the atmosphere. So you measure the phase coherence, how the signal is changing due to the atmosphere. So you have strong signal from a satellite. Instead of studying the satellite or trying to watch TV with it, you decompose it, the signal, and use it to study the phase coherence of the atmosphere. Because if the thickness of the water vapor in our atmosphere changes, if it gets thinner, the bending of the signal changes, right? Depending on how thick or how thin it becomes. So you can also do that with small, cheap instrument, less than 200 euros to build. I've got one of those in my office. Okay, if there is no other question, Chifodo, how much time should I give the students before I go to space?
Well, normally they go for break for 30 minutes, but you can decide because I think you have a tighter schedule than the students and some of us. If you want to give them less than 30 minutes, I think well, it's up to you.
Okay, so my research group weekly seminar starts in 30 minutes, and I'll need to admit people. It will just be about 5 minutes pause. I admit one person and make the person the host, and then I come back to this meeting. I wouldn't get away from this meeting because it's on Zoom. I have to start that I have to start it on Teams, so that should be fine. But we can restart whenever. I'll just take 2 minutes to admit and make one person a host.
Okay, it's all right. So let's reconvene by 1
Yeah.
by our own time.
Okay.
So that's the next 30 minutes.
Okay, good. That's fine.
Okay, thank you so much.
Thank you, everyone, and see you
Let's
soon.
take a rest.
Are you going to end the meeting in the meantime?
No.
Okay. Good. Well, Frank. Cool. Now,
Enjoyed my lecture.
Yeah, I think.
Reminds me of the good old days.
Yes.
Good old days.
All right. Yeah, let me share screen again. Sorry, now I have to juggle 2 meetings, so let's see how that goes.
Yeah.
I'll keep my volume fairly low so it doesn't interfere.
Okay.
Perfect. Okay, can you see my screen?
Yes.
I think, and it's now my pleasure, everyone, to introduce our principal today, who is Dr. Joris. Okay, can I see a thumbs up if you can see my screen and you can hear me? Okay, good. Sorry. I have, as I said, the research group seminar of my, well, the center that I lead, Center for Astrophysics and Space Sciences, is every Thursday at 2 o'clock. And it just started, but I've admitted people that I needed to admit, and I've asked someone to lead that. So I'm just making sure. If I turn off my volume, you will hear people talking in the background. Wait, okay, that should be fine for the recording because I muted this one. Okay, good. So welcome back. I have pulled out some kind of slide from ESA website, which I thought was going to be better than anything I could prepare in a very short period of time about space instrumentation. I like this one because it did not just show all the instruments, it went into some of the tests that we typically do for space instrumentation. So I think it's a good overview prepared by Tibalt. Some of the key questions you want to pay attention to is why we go to space, especially for astronomy. Also why we go to space for Earth observation. This is super crucial. Before I do this, I can show you other crucial reasons why we need to go to space. Hopefully I find a slide. There, space in Dava. Okay. I'll start with a question. Does anybody remember what this is? If you think you've seen it anywhere. Okay, if you haven't seen it, this is a satellite image of the fortification that before and after fortification method that Russia used in the war against Ukraine. They dug trenches. If you zoom into the trenches, you can see its holes, and you can actually see zoomed in image has a satellite picture of a soldier near one of the trees. And they have made this other new thing that they call the dragon tooth. This is to prevent tanks from crossing over and attacking. So if you make it across the dragon tooth, then you meet with people who are hiding under trenches to fight. Here is the second thing. Nothing rattled the world in the beginning of this year more than the precise extraction of the president of a country carried out by the US. And these are two satellite images of those two of the same site. And you can see how the building structures in red with red roofings were completely decimated by airstrikes prior to the extraction of, well, some of them prior to the extraction, some part of it was hit after the President Maduro was extracted from this heavily fortified, heavy military base. In fact, many military equipment destroyed, and there was smoke rising from this site for many days after that event. This shows you what space science and technology can do, not just for astronomy. I like to focus on the astronomy parts, but sometimes when I get broke, I write computer programs that is used in processing image for other purposes. So there is lots of use of space science, and I have recently been invited by the Kingdom of Eswatini to develop their national space policy. That's where I gave this talk. But I want to focus on astronomy because the other things people do with space sciences can be very depressing. It should be for good. There are so many good uses of it, but there are also fairly bad uses. Wait. Okay, cool. I'm muted. Nice. So why should we go to space? Space is important. Lots of things doing it from the ground can be terrible. Especially for astronomy going to space. And if you remember the EM spectrum that I showed and the atmospheric window, many of the EM spectrum released by galactic and extragalactic objects are obscured by our atmosphere and everything in the upper layers of our atmosphere. If you want to build a space instrument, what do you need to do? What are the examples? So I found this slide quite useful and informative. Okay, so why do we go to space for astronomy? It is because the atmospheric window, wherever you see anything brown, this is similar to the picture I showed in my previous talk. The atmosphere won't let you. The opacity is 100%. It means it's completely opaque and you will not detect anything. So you have to put the telescope in space, essentially. So here are ESA fleets of satellites or telescopes that is up in the sky. And there are many of them. I can describe each one of them, actually. LISA is a LIGO instrument. Is a precursor to detect gravitational wave. Planck, many of you may have heard about this. It works in the microwave band, and it was what we used to detect, to make the first map. I think it's the W map, to detect cosmic microwave background and determine that the temperature is precisely 2.75 Kelvin. Herschel is very useful. It's looked at the dust in our cold universe. It's in the sub-millimeter regime or close to infrared. And it was the telescope that told us, or that informed us, that yes, we are aware that we have filaments in our galaxy, in star-forming regions, in giant molecular cloud. But Herschel revolutionized this by showing us that filaments are literally everywhere. So there are hot, dense, narrow, elongated structures everywhere we look within our Milky Way. And I suspect same for within other galaxies that are forming stars. JWST doesn't need any introduction. It's already produced first light. Actually, if you like to study JWST if you stop hearing me, please can someone raise their hand, especially those in the ICT room, the host. Seems to me my network is slowing down. I don't know if it's mine. I'm seeing a slow network signal there. Can everyone hear me?
Yes, we can hear
Yes,
you.
sir, we can hear you.
Okay. Okay, good. Good. So JWSC is 4 years old. 5 years old. 5 years old, yes. 5 years old, 2021, December 25th. Launch, got first light a few months later. Everything's going beautifully well, is revolutionizing science. Euclid is aimed to explore the dark universe. It's making very important maps of the universe. I think the first data release happened March of last year. TIOP is for characterizing exoplanets. Gaia is our best friend for measuring the parallaxes to billions of stars. This is the first one to tell us how far many billions of stars are from our solar system. HST doesn't need any introduction. Everybody knows about it. XMM Newton is an X-ray telescope. And is doing impressive science measuring hot gas and the X-ray emission it releases. There is the integral, which goes in the gamma ray band, X-ray gamma ray band. I think TeV bands. So these are all instruments. Of course, these telescopes are expensive. I think the JWST, I don't remember if it was $3 or $4 billion that it costed in the end. So these are expensive instruments. Please, so give me a moment, please. Hello? Okay. So they are typically expensive. So no one space agency claim ownership. Everybody claims ownership if they contributed or they are involved. But if you go to NASA and ask for their fleet, you will find exactly the same, or maybe plus one or two. There's hardly any space program or a space mission that the two agencies are not involved in. So for measuring gravitational waves, I guess this is the only one you probably haven't heard. You can do it from the ground, where you can use the LIGO instruments to try to detect the bending of space-time using gravitational waves detectors. This already has been demonstrated, and I think yeah, huge press release and a bunch of other things they've done. And you also could try with space interferometer, where you can measure the time, short time lag in space using interferometers. You can also use pulsar timing, For those who do pulsars, the timing and some of the things you consider as glitches and or irregular glitches may actually be bending of space-time. And of course, the cosmic microwave background, the map you see there is the map of the W map. In principle, all you're trying to do in detecting these gravitational waves is to see how the signal or the bending of space-time generated as a result of binary black hole system interacting or compact binaries within our galaxy and beyond interacting or compact objects that are just captured by black holes or neutron star supernova rotation and so on. These are the things you want to measure because they affect space-time. In terms of space applications, there are many. You can classify them as the fundamental and applied science and technologies. For the fundamental science, whenever you use space application to do astronomy, you're doing fundamental physics or fundamental astronomy. We consider solar science now as space science because a large fraction of the study of impact of solar activities on our society, for example, impact on communication, deal with just measuring how much coronal mass ejections or solar flares or particle accelerated from the sun hitting power lines or communication systems, how much they impact them. So this is probably more of the applied science. There is, of course, space applications in human flights. This has become very huge. It's a huge tourism business now, where you get people like Blue Origin and SpaceX, Elon Musk, and essentially Jeff Bezos. Put people in rockets, get them into orbit or get them into space. They get to experience everything in space, and then they bring them back safely. Of course, it's a beautiful way if you're a billionaire to enjoy your vacation, get into space and see the globe from a different perspective. If you can see the Earth as a tiny ball from a far distance, then that would be a beautiful sight. I would like to go on that, but only when I'm older, when I'm happy to take more risk. There is exploration part besides space flight. The exploration part has to do with sending engineering systems to places where we cannot send humans, like the Mars. Mars is not habitable, way too hot. There's probably no oxygen at all. There might be some water, but we don't know how much. But we can send rovers and a couple of devices to explore those and tell us more. The other thing you could do is to observe the Earth. This is very crucial. And when you observe it, you can use it to solve societal problems. Navigation, you all use this. If you ever open Google Map while you're driving or while you're going somewhere to check where you are, which route is the fastest and so on, you're already using GPS antennas, and you're already using geopositioning systems, the GNSS systems, and so on. Telecommunication, this is already huge. Elon has put in 10,000 satellites, low Earth orbit satellites, with which he provides data, okay, provides you access to internet. Of course, there is also the Turaya phones that has been there for more than 2 decades. They are satellite phones. You make phone calls from everywhere, provided you're in the line of sight of the satellite. Okay, of all these, so what I want to do is mention some of these applications. I can show you real example of what you could use these things for. There is a project that I have recently developed. When you become broke, you look for something to do. So my university has an MOU with Star Vision, which is a satellite company. They've got satellites with very high resolution, 0.5 meter resolution cameras, and they can provide images of locations. This is one of the images they provided, but this is of Namibia. So because I write machine learning algorithms, which is essentially artificial intelligence, you could use it to solve problems. Here's one problem. Of course, if you've been to Johannesburg, I live in Johannesburg, but not in the crime-infested area. Or Cape Town, what most people see is the beautiful city, but what they don't see is that there is informal settlements, which is called shacks, where people build houses like this. Okay. In fact, the government don't know how this starts. Typically, one person goes, uses zinc, build a 2 meter by 2 meter by 2 meter cube house. There is no ceiling, nothing, just wood and zinc. And this it starts with one, gradually it spreads all over the place. There is no planning, no infrastructure. Of course, if humans live, they produce waste, no waste management systems, and the government don't know how to manage this. So I told them, yeah, I can write codes that can use satellite images and fix, and then inform you what to do about it. So this is how it starts. It starts with blank place, and then suddenly you have a very well expanded shack. So the machine learning algorithm I wrote is to work with StarVision. They provide me the image. I wrote a model that can take image from the past and image from the present, and then compare the two by identifying places where the area has changed. If you look at this image, this is a simple one by eye. You can tell that there has been construction on the in the middle panel on the top right corner. So my algorithm can identify those spots where there has been construction. So with this, if you take this model, implement it on the satellite images of areas with shacks, you can actually see what it looks like before, see where new ones have popped out, and inform the government of how much the population in the area may have increased and how much power supply they will need to provide and water and drainage. Otherwise, they should expect disease outbreak. And of course, if it breaks out in one place, it will spread to other places. I think we all learned this during COVID. So the code works. United Nations Habitat heard about it, and now they want to use it to track people who are displaced. I may want to implement this in Nigeria at some point and use satellite images of Nigeria. I have access to very high resolution satellite images, but they are expensive, so if I have to use it for anyone, they have to pay for it. Okay, so I've got the highest resolution image of Namibia. I told their president that I know your country better than you. He doubted me. I zoomed into my map and showed him that I can see humans right in this area, so I can trace people that much. Okay, so remember that the reason why we learn is that we want to solve societal problem. If you're learning for fun, that's not a good thing. Whatever you learn, every single knowledge is power. Try to implement it to bring solution to some kind of problem. Yes, I know Nigeria is battling with security problems, but that is very political. If you want to solve the security problem of Nigeria, it would take less than 48 hours. Okay. So leaving that and going back to astronomy, which is a more fun thing to do, there are a number of instruments observing different objects, some of them probing the sun. The SOHO is very popular for some of you who remember. Oh, where's this NASA guy? I forgot his name. It's ringing in my head, but it's just not popping out. So they built this instrument. I think I was still first or second year student at University of Nigeria. And they have been observing the sun. And each time you have these prominences or coronal mass ejections, they have true pictures of it. And they can already predict how long, because they know the travel speed, how long it will take to hit our Earth's atmosphere. And if we're fortunate, the magnetic field around the Earth prevents it from hitting us and then creates aurora in the northern and southern pole of the Earth. We've also sent satellite probes around many of the other planets Venus. There's the Venus Express. There's JUICE that's gone to look at Jupiter's moons. There's Cassini. There's Rosita. There is now E Rosita again. There's Mars Express. There's Cluster. There's the Solar Orbiter. I think this orbiter, there's a new one we call the Parker Space Probe, Parker Solar Probe. Okay, so these are all instruments. I think I've shown that before, but in terms of science, you can start to classify any of these space instruments into the bands at which they operate. For example, Hubble, which is our oldest one, and actually the most, probably the most expensive one, because you remember that there was a problem with Hubble's and astronauts had to be sent to go and fix it. So this has been there since 1990. I serve in the proposal review board of both JWST and Hubble Space Telescope. This instrument are still functioning. You can write good proposal and they will point if you are successful, they'll point the telescope at the source you want to see and provide it for you. The SOHO, Solar Space Observatory, has been there since 1995. SMM Newton has been there since 1999. The cluster has been there since 2000, Integral since 2002. Of course, excuse me. One problem with satellites is, if you lose control of it, that's the end of the story. They are expensive. If you're fortunate, it lasts long. Hubble has really, really surprised everyone. Of course, it has had to be maintained and a few things changed, but it's the surprise of the century, actually, of the half century. Okay, because it's been there quite a long time. Cool. So in terms of these instruments, Hubble operates in the visible, UV, and very close to the, I think, the near infrared. Okay. And then the SOHO simply picks up particle acceleration. SMM Newton is an X-ray, has got an X-ray detectors. And then the cluster looks at the magnetosphere and if you know what we call the dynamo effect. So in principle, this is space physics. And then Integral does both gamma rays, X-rays, and visible light. Look, in building a satellite is just a piece of machine, right? The payloads you put into it is what is important. In the case of Hubble, is a 2.4-meter optical telescope that it carries. In the case of the SMM Newton, it carries X-ray detectors. So if X-ray photons come in, they have detectors that are incident on it. They incident on and then they are picked up. Okay. But if you have more space, for example, the SWIFT, there's a space telescope we call SWIFT telescope. It can do both X-ray, UV, and optical. So it simply means you put a CCD camera that covers the optical band. There's also X-rays can be picked up with CCDs, but X-ray CCDs or X-ray detectors. And then you put UV detectors and then you're good. But remember, you're taking this to an extreme environment and therefore it needs to be tested. I think I'll show that towards the end of my talk. The Mars Express focus on studying Mars and its moons and its atmosphere. Gaia is, for me, beside Hubble and JWST, is the next one that I like so much. I don't know, between Gaia and Spitzer telescope, because Gaia, I've done astrometry. Astrometry is how you measure distances to stars. Remember, I told you being born in the Milky Way is similar to you being born inside a large building. And if you're inside that building your whole life, you don't know what the building looks like on the outside. So we're born in this galaxy. We have no idea what our galaxy looks like on the outside. Our solar system, we can tell, but our solar system is a tiny, minute, insignificant dot in the scale of the galaxy. So if you're in the house where you were born, right inside, you're not allowed to go outside, and they give you a paper and a pen and say that you should draw what the house looks like outside. I guess the only option you would have is to measure the distances to the edges of the building, and then you can start to sketch what you guess is the shape from the outside. That's exactly what we're doing. We don't know what our galaxy looks like. So we're measuring distances from our own solar system to many stars, thousands or billions of stars in our own Milky Way. And we're using that distances and the 3D morphology distribution of these stars to reconstruct what our galaxy looks like. I have slides and a separate talk for that, but not here. LISA is a pathfinder for detecting gravitational waves, which was launched into space. BEPI Combos is for exploration of Mercury. It was launched by JAXA. JAXA is Japan Aerospace Exploration Agency. CHIOP studies exoplanets. There is also another one. There is the TESS. The TESS telescope also looks for exoplanets. There is solar orbiters studying the sun. JWST essentially to find the origin of our universe. These are no longer upcoming. Remember, these slides are quite old. Pluto had been launched. Athena is still up and coming. Gravitational Waves Observatory is still up and coming. This is a replacement for LISA. Pluto was launched last year, if I remember correctly. Euclid is already producing data, and the aim is to use it to understand dark matter and dark energy by measuring a huge sample of galaxies at very high redshifts. High redshift just means high distances. There is JUICE. This is very important. There is a moon of Jupiter that seems to have a lot of water by analysis of data from the observation. And the aim here of JUICE is to be sent there. I think it was launched. I don't know if he has gotten there. So I don't keep track of the space probe, just too many. Any questions so far? If there is, please raise your hand. Otherwise, I wouldn't know.
Now, for basically a little bit of a coincidence, this.
Okay. What I hear is the other talk. I assume there are no questions. Let me see. Nice, none. Please use the raise hand option if you want to speak. Okay. Aman, please.
Good afternoon, Professor. What I want to try and to understand is like,
Okay,
how
go
does...
ahead.
Quite a bit lower than the original estimate of 11.
Oh yeah, speaking or I can speak.
And just a fun note, I think, is that this galaxy.
So I was trying to say that what I'm trying to understand is how does these satellites that you're talking about link with the previous presentation that you were talking about? I kind of don't see the link. Maybe if you could maybe summarize or try and explain so I can understand the link between the two, because it's like two different topics.
But we followed this.
Okay. Do you mind typing the question? Because...
Okay, I'll type.
Okay, wait. No. Aman, can you type the question? Because I've got another meeting going in the background.
You want me to type it?
To be disrespectful and exit that meeting. So just type the question, I'll read it and then respond.
Okay. Okay. I'm typing
I'll
it.
just continue while you type. Others can please do the same. Okay, so I know you may be wondering how does LISA detect gravitational waves? So LISA is a plan to put 3 instruments in space, okay, that measures length variation, okay? They are constantly synchronized, okay, to have the same separation. If for any reason they continue to take measurements and they see a change in the length between these two, then that in principle means that space has varied, has changed. And that's an evidence of gravitational wave passing through the environment. Okay. Let me stop and just check if there are messages. Yes. What is the link between satellites and radio astronomy telescopes on Earth? And what is the link between the two? Please summarize radio astronomy segment. Okay, so I was asked to speak about instrumentation in astronomy and space sciences. For astronomy, I could speak about instrumentation in radio, optical, infrared, X-ray, UV, gamma rays, not in any particular order. But I focused on radio because I'm a radio astronomer. I'm biased to radio. But also the focus on radio is because you need radio for satellite communication. The images taken by X-ray telescopes are transmitted to the ground so that people can load it in a computer and process it through radio waves. We don't send the images via X-rays or gamma rays. Those will not penetrate our atmosphere. So the principle I have shown in radio observations and the instruments and the backends you use is applicable to satellite communication, okay? You take data in any band you want, you embed it in radio waves, and you transmit it, just like I can embed anything in the cloud and then you download it if you have internet. Okay, so that's the first link. In my first talk, I skipped one part of satellite communication. Let me see if I find that. Wait, just give me a moment. Yeah, I didn't describe it, but I can do that. Where is it? No, no, no. Did I close that? Strange. Okay. Trying to show something else where we use satellite technology. It's not here. Okay, I wanted to show you that in the principle of interferometry, okay, so remember I said earlier on that we want to make the dishes very large because it helps our angular resolution. Angular resolution is theta. Okay. So if you compare angular resolution of the eyes, because the wavelength is very short, okay, and you divide it by the diameter of the light sensitive part of the eyes, which is the pupil, and is 1 millimeter in size, you get an angular resolution of 2 arc minutes. 1 degree is 60 arc minutes, okay? So this is like 1 out of 30 places of a degree. But if you build this huge telescope, which I've shown you a short YouTube video of, which you call the Green Bank Radio Telescope, you achieve the same 2 arc minutes after spending almost $2 billion to build that. Okay. The HST you saw in space will achieve way better resolution in milli-arc seconds. Well, you need 60 arc seconds to get 1 minute, but you will need to divide 60 by 1,000 places to get 1 milliarc seconds. So just a small telescope of 2 meters in optical gives you extremely high resolution. Of course, the problem is the wavelength we're observing at, the lambda is large for radio. Therefore, the only way we can improve our resolution is to increase the denominator. But there's only a limit to how big dish can be. So the concept of interferometry, which I didn't introduce because of time, was introduced by Martin Ryle, who won Nobel Prize with Antonio Hewish. If you're Nigerian, you should be probably racking your brain, because Antonio Hewish, who was 1974 prize winner, was the supervisor of the first Black African astrophysicist, Professor Samuel Okoye from Nigeria, late Professor Samuel Okoye, who during his PhD published a number of Nature papers, which is a record. And Hewish was his supervisor, and also the supervisor of, my brain is tired, so I'm not remembering names now. The lady that is great, Jocelyn Bell. Yeah. So she's still alive. She's there at Oxford. I met her a couple of times there. And yes, this prize shared with Anthony Hewish was for the principle of interferometry, which says instead of trying to build a 200-meter parabolic dish, which is completely impossible, 200 meters is the distance between, if you are in Nigeria, is probably Onisha and Port Harcourt, most likely. Yeah. So one dish that is that huge. So you know that is not possible. Then you need to build small dishes and spread it over the area and use them simultaneously to observe a source in the sky and combine the data intelligently. What you see on the top right is actually a telescope I use for my PhD. There are only 4 telescopes. I know in one of the pictures you see 2, only one of them is used for this array. And if you combine them and observe together, is equivalent to a single dish that has a diameter of 2,300 kilometers. That's about close to the full length of Japan. Okay, so if you do this, then you can change D by B, where B is the separation between the antennas. Then B becomes very large, and therefore theta becomes extremely small. And we call that very long baseline interferometry. So astronomers did this. They were happy, they celebrated, but eventually they wanted even longer baseline to have better resolution. Then they put a radio telescope in space. And now the separation between the two, the things observing from the ground simultaneously with the satellites, which carries a radio telescope, but observing in space, the separation between them was close to 400,000 kilometers, which is impressive, gave us among the best resolutions we've ever seen. So that's a link to radio astronomy. We use space technologies to enable improved resolution for our research. I don't know if that helps. Of course, radio astronomy helps space science because we use it for tracking the satellites. We use it to downlink the data. You also use it to uplink instruction. Remember, you move the telescope or the satellite. You can tell it to
Yes,
move
and does this
outward into
also link
orbit
to the
or inward.
previous
You can
slide?
also, when it's
Oh,
about to die, drive it into the Earth's gravity so that it just burns out in our atmosphere. If it doesn't, it will hit the Earth just like the one that hit Kenya recently.
I'm saying on the previous
Okay,
slide,
please, if
the
there's
one.
any other question, put it on the chats. Okay, so Lisa, when it was launched, people were just hoping it would get a few signals, but it definitely outperformed what was expected as a precursor instrument, but I don't think we need to focus on that. The Rosita, many of you remember this, when you have to chase an asteroid to go catch a piece of it. A lot of people are already secretly planning to send rockets, satellites to some asteroids to collect samples. Some of them have collected samples processed and they want to commercially mine those asteroids. Don't ask me if they're allowed to do so. If you go in the outer space, most of the outer space laws are not binding. They are more like admonitions. Do it if you like, or follow the rules if you want. So in principle, if you have money, you can send a satellite to space, pick any comet you like or asteroid you like, send your satellite to it, drill a hole into it, attach to it, drill a hole, collect a sample, bring it back. If what you brought in is a metal we've never seen before, you can put it at the price of $10 billion per ounce and you could still sell it. So astro mining is now quite a big thing. There may be people who are already doing it secretly because there is no need for any license. You just have to launch a rocket and then bring it back. Okay, Earth observation. I showed that this is one of the key things you want to do with satellite instruments. It's crucial. We're studying distant universe, but we're yet to understand fully our own planet. And there are many things to study about the planet, and there are many Earth Explorer instruments that have gone up. Some of them are still there, some have died. Yeah, like the GOES project, which lasted from 2009 to 2013. If you're wondering why a satellite mission would die, it could be that you fail to reconnect to it, or you send instructions to do something and you no longer have connection. Or it was a satellite built with a tank of fuel, okay, to power it. If the fuel runs out, the satellite is no longer able to move. And then it will be thrown about by whatever happens to it with the gravity in the environment. So, but GOES GOCE was there to study the Earth's gravity field. SMOS is there to study the water cycle to see how evaporation happens on a large scale and how water condensates and then fall like rainfall, drops as rainfall. If you go to the South Pole, you still have Cryosat 1 and 2. 1 is packed up. Cryosat 2 is still functional and is studying the ice cover over the poles in the Arctic and the Antarctic. Well, yeah, don't remember the one for Antarctica. Okay, SWAM is still there, studying the Earth's magnetic field. ADM looks at the global wind structure. EarthCare looks at our cloud, measures our aerosols and radiation. This is where one of the satellites, Earth Explorer, that provides us information about climate change. Of course, you can see now that in recent times, you wouldn't find NASA in any of these climate change mission because President Trump doesn't believe in climate change and decided to defund some of these projects. Biomass, things studying the carbon cycle in the system, and then photosynthesis, the process through which green pigments generate energy in the system or in plants. Okay. So if you're ever looking at the green distribution, how it changes over time, and how much that impacts the quantity of oxygen and the extraction of carbon dioxide, then you need to look at the flex data. There's also Explorer 10 and 11, which eventually ESA, I don't remember which one they chose, but they choose by numbers and then names are given to it depending on specific goals that it needs to achieve. There are also satellites you launch in space just to study meteorology. If you ever open your phone and go to, let me see if I can open that now and show you. If you go to your weather app on your phone, you can actually now with the weather app show the cloud motion or the cloud distribution pattern. Let me see if that launches now. So that's Johannesburg. If I scroll all the way, there. So these are all satellite images that are converted into a format that you can look at it from your phone. I do hope you can see my camera. And this tells you the precipitable water vapor content. If it's very yellow, there is dense precipitable you can see on this spot. If you see my finger, that's where you have more water vapor. So it would likely rain around that area. Okay. So yeah, so Johannesburg have no chance of rain. That's where the number is. There are no rain clouds based on satellite images, and meteostats is one of those that are very, very crucial. Yeah, I can mention this, but I was recently asked by British High Commission to train 30 Africans on how to do startups. And one of the projects that a group is doing is how to use meteorological data to inform farmers when to plant. Because if you have information of how the clouds are moving and how they move over the next 2 weeks, you can tell farmers that the rains are coming, it's time to plant their crops, and so on. You can do lots of things, so, and make money out of it. Okay, not sure how much more time I have, but you can also use, let's see. But if you also have ones for global monitoring, this is essentially for safety. You have the Sentinel satellites. If you go online, you can access data from Sentinel for free. You use some of these instruments to monitor climate change, to store the data so we can, over time, check how things have varied and so on. So Sentinel is actually a very useful site if you ever want to use satellite images to do proper science or to study something. Okay, that's still about Sentinel. Now we go into the specifics of building an instrument for space. Space environment is not the same as the ground environment. If you want to put something in space, is huge. First, it starts with planning, what exactly you want to do. Well, in the planning phase, you need to determine whether you truly have to put that object. Remember, it's expensive. very, very expensive to put something in space. A proper satellite, a medium-sized satellite will cost you up to $3 million to make. A CubeSat will cost you, one new CubeSat will cost you both launch and everything about $300,000. So you don't just put things in space. That's what I mean. You need to plan, because if you're putting something in space, you need, for example, the engineers who will build what you want to put. You will need a control room where you will control what you have put in. You need contracts for people who launch satellites. Okay. So the launch pads are very important. And as I speak, there is none on the African continent, despite Africa being very close to the equator where you can easily just get into orbit. But strangely, we don't have any. So if you know any billionaire in Nigeria, tell them that just building a launch station could make you even richer than anything, because people will bring their satellites and then you launch them into orbit. So you need launch facilities, you need people who build the instruments, you need your ground segment, which is your ground station. You need, of course, in the ground station, you have your control center within that. And then you have your data management center to uplink. To send something to the satellite, you must have an antenna down on ground, through which you just convert whatever you want to send, be it instruction to tell the satellite to rotate or point in a different direction, or be it software upgrade, or be it trying to resolve some software problems. You need to, log in and send all those signals up there. Then there is also the downlink segment, which is the user segment. In the case of communication satellites like that of Elon Musk, the user has this small white antenna they put on top of the roof, and then you connect it and you get access. But if you're doing remote sensing, what you need to bring down is pictures. So in that case, your user remains either yourself or people you give access to whatever the repository of your satellite is, so they can download the data. So yeah, it's huge. It's not trivial. It's not something you can just go off the shelf and pick it up and then you start running with it. Needs adequate planning. Well, each time you see a picture of a satellite in space, is made up of different components. You have the satellite itself. Definitely you need a power supply system. Most satellites that you want to last very long, and yeah, in the orbit, carry solar panels. Well, this is quite new. Remember, the solar panels for power generation has been super expensive and difficult to use for a long time. So the earlier satellites only had solid or liquid fuels inside them. So they carried tanks that contain the fuel that powered it. But now you could do that with, batteries and solar power systems just to drive the satellite. The satellite in itself is one thing. The payload is a critical thing. The payload is where you put in the instruments. If you're an astronomer, you put a telescope. If you're a non-astronomer and you are just interested in remote sensing just to do imagery of the Earth, then you put in a camera, high resolution camera, with which you can zoom into the Earth. Okay. Cool. So if you plug in all your payload, there must be a way to the service modules include your power distribution systems. These are the basics. Okay. You need your control system. You need a gyroscope, which will balance the satellites in space and tell you where it is. You need a star tracker. You need a propulsion system, which is mostly in this system powered from solar generated power. You need telemetry. Telemetry is how you know where your satellite is. There's a story I always tell when I talk about this, that the Europeans launched a satellite at one point and they lost it. We used the telescope in Hadbistook to find it for them. So that's quite useful. And then you need skills in data handling. You need to prepare how the data you collect with your payload is sent back. All these are carefully tested one by one, confirm that they are working before you package the full satellite, run all the climate tests before you take it to a launch pad, load it into the rocket, and wait for the countdown day. So that makes this very rigorous process. JWST, I don't remember the date, but it took more than 10 years from the planning and conception phase to the date it was launched, because each one of these is developed separately. Remember the shape and of your satellite, the payload you carry is something you sit among the funding organizations and the engineers to decide. So for a space mission, it has a life cycle. The life cycle starts with phase 0, where you analyze the mission, identify it, and think whether you really want it. And the phase 0 is just identifying what you want to do. Phase A is where you do the visibility study. The fact that you have money to buy a satellite and put it in some orbits does not necessarily mean you have an orbit where to put it. Some orbits are taking. The Eswatinis, the Swatis, have just started clearing their orbit, paying to reserve where their orbit would be. Okay, so phase B, when you check the visibility and you're happy, you start to define the preliminary conditions for launching the satellite. Phase C, you do a detailed definition. Phase D is when you go into qualification and production, and of course, launching. And then phase E is when you start to utilize the satellite, if it's still functional, if everything is successful. Phase F, which almost nobody does, is disposal. What people don't know is that currently, as you see in the picture on the bottom right, we have over 1 million objects moving around the orbit. Some of them, we know they are still active satellites, including the Hubble Space Telescope. Okay. Of course, the orbits are all different. You have low Earth orbits, you have the geostationary orbits, and all the other orbits. But there are everything that humans have thrown into the orbit are all there. What people don't do is when they lose their satellites. For those of you who are old enough, you may remember when Nigeria said they launched a communication satellite, and 2 days later they said, no, we cannot find it anymore. Of course, in Nigeria, you always have conspiracy theories. People said the satellite wasn't launched at all. Some said it was, but they just lost communication with it and so on. Yes, you could lose communication to a satellite. Could be newly launched one, it fails. But the object is still in the orbit. Where it is, you don't know. It's just somewhere flying around. Okay. Of course, you can think of all the things you could try, but if you don't connect to the satellite, you've lost it completely. It's no longer yours, it's nobody's. Now, in such instance, that object just keeps flying around and could sometimes by chance re-enter the orbit, re-enter the atmosphere of the Earth due to the gravitational pull, and then burn out in the atmosphere. If it doesn't burn out completely, it will hit the ground. Now, there has been laws trying to mandate people who put satellites in the orbit to make sure that when they are done with the mission, that they remove it from the orbit. This is mostly a European effort. I hope they succeed because I guess we're already struggling with the number of things in the orbit. But the policy simply says if you launch, use, you must dispose. And there are companies, there are big businesses building satellites that can just go to orbit, follow your own satellite that is out of use, suck it in, and re-enter the Earth's atmosphere and burn out. That way you've done disposal. Okay, we're running out of time, and happily I can exit the other meeting. I think it's ended. Oh no, it didn't. Okay. But now I've increased the volume, so you can talk now. So the organization of a mission starts with the scientific community. You have to propose some concept. For example, the JWST people wanted to have the most sensitive infrared instrument, no obscuration from atmosphere, just put in space and point and integrate it for a very long time and detect the very, very early universe. Of course, when you conceive that, good for you. You've created a problem. People in the industry, astronomers don't build telescopes. It is the engineers in the industry that come and say, okay, if you want to do this, this is what you require. Then you bring the agency in. They are the people, the customers, they will pay, and they will operate it when it's built. And then they are responsible for the launch. So the industries will manufacture different components. Remember, when you bring a satellite, it has some satellite, depending on the number of payloads, can have up to 200 components. And these are all subcontracted to different experts in the industry to build. The agency brings it all together, does the testing and launches, and then operates and then uses it to service whoever. The member states of ESA of Europe will be able to assess the payload that they are responsible for. Okay, I want to go straight to testing just to show you true pictures of some of the things you do in terms of testing. Of course, this is a satellite, real satellite that went into orbit. And you can see they are brought into different environment and tested for different things. One of them, for example, this, which was launched in 2013, the Gaia. This gave me a nightmare because it used to take me 1 year to produce one parallax. And they said this guy was coming online and was going to produce billions of parallaxes. So I was worried, but I got my PhD before that. But VLBI parallax is still better than this. Okay, so what parallax is, you can read up at your own time because I want to show you why we need such parallaxes. Okay, this is a real picture of the footing of Neil Armstrong on the moon. Okay, so if you talk about a parallax that you can measure with accuracy of 10 microarcseconds, it means being able to stand on the Earth, look at the moon, see the footprint of Neil Armstrong, and be able to see the soles, like the gap between the lines under the sole of the shoes, of the space shoes he was wearing. So that's really accurate. So if you project it to longer distances, we can accurately measure distances to stars. But for these spacecrafts, which we usually show as a tiny little thing, that's how huge it is. Okay. And this is a lab where where it was placed on a pedestal and then they'll wheel it around to do different tests. Of course, eventually it will be wheeled to the rocket to take it to the orbit. Here are the payloads that were in Gaia. Most of them are just optical CCD cameras and optical sensors, and also sensors to balance it and tell it where it is so you can tell it which position to point. I won't show all the instruments. I like to show the tests. This is just testing the photometers. That's the things for measuring photometry, the CCD cameras. This is for the velocity, radial velocity spectrometers that splits light into multiple parts, and then you can measure the full spectrum. But what I want to show you are the tests that you make just to be sure that you're doing the right thing. This instrument here, this piece of instrument that is on Gaia, is used to monitor the angle of tilt. So it's a sort of interferometer that whenever the satellite tilts, you can measure the tilt angle. You can monitor that angle with these two devices. Again, that alone is probably a couple of millions of dollars to build this instrument only. Okay. And then it's one module that goes there. There is the thermal balance. You have to check for heating, thermal vacuum system that is properly tested because you're going into extreme environments. There is vibrational test. Remember, you have to put this in a rocket and launch. Okay. That picture there, this is actually the real launch of Gaia telescope. Okay, there's a true picture. And this creates a lot of vibration. You want to make sure that all the pieces you have put together inside the satellite, when you introduce it inside the lab to the same size of vibration that the rocket will create on the satellite. And then you go back and check all the systems again to make sure things haven't fallen apart. EM compatibility, this is super crucial. What you see in the background are absorbers. So things with which you make sure that there is no external radio emission coming inwards. And then you can measure, you can try to transmit, okay, and see how much EM leakages come from your antenna. You have to report that to the International Telecommunication Union. They have to look at the report before they approve launch. You also do acoustic tests just in preparation for launching. You check for leakages, leakages of all forms. Okay. If there is, for example, a vacuum chamber, something that sucks out hot air, you can check if it's doing it properly or not leaking into some other pathway within the system. Okay, you also do solar shield. The sun is very harsh on anything above the sun, above the earth. Keep in mind that this will constantly be seeing the sun. Right? It's not on the earth so that if the earth rotates, then it's on the other side. So because it's above, there's always line of sight with the sun. So this is one test you run. Excessive exposure of your electronics to the sun can fry it. I mean, fry, yes, it would just kill it because the heat is too much for the electronics. Okay, Gaia was successfully launched and it has produced millions of parallaxes of stars, distance to stars. You can go to the archive, take the data, use it to do all this research you want to use it to do. And I will stop there for today. Thank you. I'll take questions.
Yeah, so much, Professor James. No, continue to work on and on for several hours. You are used to that, and we know. However, we have to stop because we don't want to overstate the principals. So thank you so much for that wonderful talk. And maybe you take one or two questions quickly, and then we're done because we're already into people's time.
Yes, we're 30 minutes.
Yeah, top one. Please. Aman.
I can speak, or do you prefer me to type?
You can speak now.
Yeah, you can speak.
Okay. So what I kind of want to ask is that you're saying that the radio astronomy based from what was from 1932 from, you say, Bell Lab Company, right?
Yes.
Yes. So how does Lab Company in 1932 linked to a square kilometer array in Africa, and how does that help Africa have a Nobel Prize? And another thing which I like to ask nicely is, what are hydrogen bridges? And could you show a picture of what a hydrogen bridge is and what the Milky Way jet is? Because I'm kind of, yeah.
Okay, cool. Nice. Thank you. Good questions. Let me open a very good slide for that. So the square kilometer array is a plan to build 1 square kilometer, as I said earlier on, right? And then it's going to revolutionize science. It's going to change everything we know. Now, how that started came from this history that I showed you earlier, this tiny history. So remember, humans are insatiable, right? If you give them $1, they want two tomorrow. You give them two, they want five. Give them five, they want 10. So we started with these people who were looking for man-made signal, but they found signal from our galaxy. Okay, and then somebody decided to build a proper telescope to observe the signal from our galaxy. And then another one built a bigger one so that we can now start to resolve sources in our galaxy. In fact, at this time, we did not think that any radio waves came from outside our galaxy. If you read stories about people who did radio astronomy in the 1940s, we thought every radio emission is just from our own galaxy. So we started to see even things outside our own galaxy and built interferometers. And now the plan to build the SKA came. The bid of where the SKA will be built was the most intense bid I have ever seen as an astronomer. Countries were lobbying each other. America was lobbying to build it in the US. Australia bidded to host it. Some part of Europe bidded to host it. South Africa was the only African country that submitted a bid. Of course, the condition is you must have a good site where there is radio quietness. To be radio quiet, you need less population. So the site for the SKA mid is in the Karoo Desert in South Africa. When the decision was reached that South Africa will host it because they had the best site, and then they had the most positive bid or justification to have the telescope. Two countries threw tantrum. America stepped away. America is no longer part of SKA. They decided they are going to build the NGVLA. VLA is a very large array. So NGVLA is new generation VLA. And they already have the proof of concept. They want to build it in the Northern Hemisphere. So America is not part of SKA consortium. UK is still part. Germany was part. They dropped out. They came back again. France is there. Australia, that also bidded, they had a very good site, but they did not win the bid, and then they wanted to leave. So what the consortium did was to split SKA into two, SKA mid frequencies and SKA low frequencies, and gave Australia SKA low. So there are now two sites for the SKA observatory, and UK, which is a major partner, is where the headquarters of the SKA is. So Jodrell Bank Observatory is the SKA headquarters. So 3 sites, 3 locations, 1 observatory. Again, that's a political side to things. Now, why do I think this is Africa's best chance at getting Nobel Prize in physics? The key questions SKA aim to answer is the origin of life, origin of gravity, to prove Einstein's theory of general relativity, to prove the origin of magnetic field, to look for the unknowns, of course, to study galaxy evolution and cosmology, and all this list goes on. Okay, we have this big book we call the SKA Science Book. So you can go read that to find all the science cases. There are things, okay, that, for example, WMAP won a Nobel Prize. Black hole imaging or discovery of black hole, Nobel Prize, okay? SKA will find many of these things, and SKA is right in this continent. So we don't just want to be the host. That's the reason I came back to my home continent. Actually, I went back to my home country, but it wasn't as good as I wanted it. Is so that we can train capacity. At the moment, South Africa will get 14% of the telescope time on the SKA, but the whole Africa have less than 50 radio astronomers. The entire continent of 1.4, 1.2 to 1.4 billion people has 50 radio astronomers. And by the next 5 years, this instrument will come online. If we don't have radio astronomers who could use this and discover new things and write those interesting results that will win Nobel Prizes, we would have just become a host to instruments, and then the white people can use it to discover all the things and win Nobel Prizes. So everywhere I go, even to presidents, I'm giving a talk at the Royal Society Rising Star Africa Prize lecture on the 4th of March. That's my headline, okay? If we don't produce Africans who will use these instruments, will miss out on the opportunity to contribute to co-create the knowledge system, and we will just be only proud hosts of the instrument, and other people will win the prizes. I don't know
And
if
you said that you show what is a hydrogen bridge, and do you have a picture of it?
Yeah. Okay. So cool. That's this. I'll exit full screen so I can point. This galaxy here, you can see in the optical, it has spiral arm, right? This galaxy here is this galaxy. The pictures, the colors here represent the distribution of hydrogen gas. Okay. So if we had only optical, hydrogen gas can only be observed in the radio. We would have seen this galaxy. We know that there is another satellite galaxy. There is a satellite galaxy. There are some foreground stars. There are a few things here. You would never guess that these galaxies are interacting, that there is a bridge between them. But if you observe in radio at 21 centimeters, you make a map of the distribution of hydrogen in this region, which is the same as this region. This galaxy is this guy. You can see this is still hydrogen. It's faint. It's not a lot, but you can see it's connected to some blob of gas somewhere here, and another blob of gas, which is connected to this galaxy somewhere here. But this has a tail that connects to this galaxy. So this guy is talking to this guy through this branch. Okay, this guy is talking to this guy, and he's also talking to that guy. And this guy is talking to this guy from this gas distribution. So this guy is also still talking to this guy. You can see some gas coming in this direction. So we call this tidal interaction. I'm happy with the word you've used, hydrogen bridge. It's a bridge of hydrogen connect the two galaxies. This is not 1 kilometer apart. This is millions of light years apart. Okay. And yet there is hydrogen stretching that millions of light years and connecting these galaxies. Who knows? What if we do not know whether our galaxy is interacting with another galaxy? And someday...
Oh, it's like a celestial body or like a nebula, something like that.
Yes, it's gas, just a trail of gas.
Oh, okay. So it's not a celestial body, it's just gas.
It's gas, yes. The celestial bodies are here. Okay. These are...
Okay, and you said you'd show the Milky Way jets as well. How do the Milky Way jets happen?
Okay, so we know the Milky Way doesn't have a jet, but we recently used Meerkat telescope to discover that the Milky Way has a bubble around it. Let me see. I've got all those, but in different slides. Okay, I can't find it now. But this galaxy here, okay, is similar to the Milky Way, but has a well-collimated jet. Okay. For the Milky Way, what we have seen with Meerkat is that it does have a bubble coming out from the center, and that paper was published in Nature recently. So we think that this is some energetic processes that accelerates electrons and form the synchrotron radiation, which we pick up from radio telescopes.
And why do you need cryogenics? Like, why do you need cryogenics to maintain the radio telescope? And when you say like 24 hours, you can access this can be anywhere around the globe as well. When you say that you can do radio astronomy 24 hours, it can be done like all across the globe. And why do you need cryogenics for the telescopes and satellites?
When you make a phone call for 1 hour, what happens to your phone?
Well, Nadia, I think have up and we have so that it after this summer school. So endless and we don't have all the time. I think we have to end the session now, having injured so many people by eating their time. Sorry if you are still having some questions, maybe you direct it to Professor James when we drop his email for you. I think that will do. So I think this you have done so much, have taken so much time for this, and we appreciate you for the time, all the sacrifice you are making for this fast for food. And I think on this note, we have to end. We say it, thank you, and just as you respond, if we call on you again, we still hope that you will be there to respond. Thank you
Okay,
so
I put my email here so you can grab it and then send me your questions. I will try to reply. Thank you, Professor Odo, for organizing this.
much.
Yeah.
Bye.
All right, bye, everyone.